Hi, I'm Matt, and in this video we're going to talk about how to find higher order derivatives, so that being finding the second derivative, third derivative, and so on. So first off, we're briefly going to review how we notate derivatives. So we have the Leibniz notation, which again we're going to base it off y equals f of x. In the Leibniz notation, our first derivative we represent as dy dx, then our second derivative d squared y dx squared. Notice that here the squared is after the d in the numerator, and then in the denominator is after the x. It's important not to move the squared around because that could mean different things. And now for third and higher order derivatives, it's pretty much the same thing as the second derivative, just now instead of a 2, we're going to use n, where n is what derivative we're taking. So for example, if we were taking the third derivative, we would write d cubed y dx cubed. And in addition to the Leibniz notation, we also have the Lagrange notation, which we're again going to base off y equals f of x. So here, our first derivative is going to be f prime of x with 1 prime, and our second derivative now, we're going to have 2 primes. However, after 2 primes, it sometimes gets a little silly just constantly having primes. So for the third derivative and higher, instead of putting the primes or the slashes, we're going to put what order derivative we're taking in parentheses. So for example, for the third derivative, we would write that as f, then in parentheses 3, and then an x. So this here would be the notation for the third derivative. So first off, let's talk about what the second derivative is. So the second derivative is essentially the derivative of the derivative. So in the first notation I introduced, we have that our second derivative, d squared y dx squared, is equal to the derivative of our first derivative. So just going back to a single derivative, we know that the first derivative represents the instantaneous rate of change of the function at each point x. We have something kind of analogous for the second derivative. So the second derivative of a function f of x is a function that again represents the instantaneous rate of change, but now it's the instantaneous rate of change of our first derivative, f prime of x. So now that we know what the second derivative is, how do we compute the second derivative? Or in the notations I introduced, f double prime x or d squared y dx squared. So the first thing we're going to do is we need to compute the first derivative. And that we're going to use our regular rules for derivatives, power rule, product rule, quotient rule, etc. And then once we have our first derivative, we're then going to take the derivative of the derivative. And again, we'll use our regular derivative rules. There's no way to get to the second derivative without having first computed the first derivative. So now let's try an example of this. So we're asked to find f double prime of x, where f of x is 4x cubed. So again, f double prime of x, this is our second derivative. So the first thing we're going to want to do is find the first derivative. So I'm just going to write that. We're going to find the first derivative. So we want f prime of x. So to find f, so we know that f of x is going to be equal to 4x cubed. So now our first derivative, this will just be using the standard power rule. We're going to multiply the 3 by the coefficient of 4 to get 12, and then we're going to decrease our exponent by 1. So we get the first derivative to be 12x squared. However, that's just the first derivative. We want the second derivative. So to be short here, I'm just going to write find second d, d here being derivative. So now we want to differentiate our first derivative. So we know that f prime of x is going to be 12x squared. So that means our second derivative, f double prime of x, we're again just going to have to use the power rule. We're going to take the 2 and multiply it by the 12 in front. And that's going to be 24, and then for the x, we're going to decrease the exponent by 1. 2 goes to 1, so 24x to the first, or just 24x. Therefore, here we find that the second derivative, f double prime of x, is going to be equal to 24x. So you see here, finding the second derivative is just really doing what we've already done to find the first derivative, and then just doing it twice. So here we're asked to find f double prime of x, so our second derivative, where f of x is equal to sine of 2x. So again, our first step, we want to find our first derivative, or find f prime of x. So to do that, we're first going to write f of x is equal to sine of 2x. However, we see that we have a sine, so we should probably just write our derivative rule for sine. For sine, we know that the derivative of sine of g of x, where g of x is whatever is inside the sine function, is going to be equal to cosine of g of x times g prime of x. So again, cosine of whatever was inside the sine multiplied by the derivative of what was inside the sine. Therefore, we get that f prime of x is going to be equal to cosine of 2x times the derivative of 2x, or times 2. So we get that our first derivative is going to be 2 cosine of 2x. Now that we have our first derivative, we can now find our second derivative that we're asked for. So we want to find f double prime of x. So to start off, I'm going to rewrite our first derivative, f prime of x, which we said was 2 cosine of 2x. And now, since we see a cosine, let's review our derivative rule for cosine. So it's very similar to that of sine, except we say that d dx of cosine of g of x is going to be equal to negative sine of g of x, and then again times g prime of x. So again, very similar, except now cosine is replaced with negative sine. Therefore, we now find that f double prime of x, our second derivative, is 2, since it's just a coefficient, times the derivative of cosine 2x, which is negative sine of 2x, times the derivative of 2x again, which is 2. Therefore, overall, we find that our second derivative, f double prime of x, is going to be negative 4 sine of 2x, and that is our final answer. So now that we've done second derivatives, let's talk about what we mean by higher order derivatives. So there's no reason to stop at the second derivative. We could take third, fourth, fifth derivatives, and while it might seem like silly to go that far, in physics and in many other fields, there is use for derivatives past second order. So when we say a higher order derivative, that's referring to the repeated process of taking derivatives of derivatives to get a higher derivative. So we typically say that when we take the third derivative or higher, so third, fourth, fifth, and so on, we typically refer to those as higher order derivatives. Also, just a quick note, the third derivative is equivalent to the derivative of order 3. It's just a more compact way of saying it. So now, for example, the third derivative here would be the derivative of the derivative of the derivative, and we could think of it as being written somewhat like this. So derivative 1, derivative 2, derivative 3. But again, we're always going to use this more compact notation, or on the f with the superscripted 3 in parentheses. So now, how do we compute higher order derivatives? It's pretty much going to be the same procedure. We're first going to get our first derivative using our standard derivative rules. We're then going to take the derivative of the derivative to obtain our second derivative. Again, we'll use our normal derivative rules. And then finally, we're going to continue taking derivatives until we've reached the desired order. So that would be, we'll take the derivative 3 times to get the third order or third derivative. We'll take the derivative 4 times to get the fourth derivative, and so on, 5 times for the fifth derivative, etc. So now let's try an example. So we're asked to find f with the 3 in superscripted of x. So again, this is the third derivative. And we're given our function f of x is equal to x to the fourth plus 12x. So again, step 1, we're going to want to find our first derivative. So find f prime of x. To do that, I'm going to write f of x is equal to, as it's given, x to the fourth plus 12x. And now we'll find the first derivative. Here, this will just be an application of power rule. So we know we have a 1 in front. We'll multiply the 4 by the 1, and that's going to be equal to 4x and then it will be to the third power because we decrease the exponent by 1. And then for our second term, the derivative of 12x is just going to be 12. So that's our first derivative. Now our second step, we need to find our second derivative. So find f double prime of x. So to do that, I'm first going to rewrite our first derivative, which we found to be 4x cubed plus 12. And then to find the second derivative, we're again going to use power rule. So we're going to multiply the 3 by the 4, and that's going to be equal to 12x squared. Again, we decrease the exponent by 1. But the derivative of 12 is a constant, and we know the derivative of a constant is 0. So we get that our second derivative is just 12x squared. And then finally, for our third step, we're going to need to find the third derivative. So f with the 3 in parentheses, x. So to do this, I'm just going to rewrite our second derivative, which we said is 12x squared, and then we're going to differentiate that to get that our third derivative is equal to, again, we're going to use power rule, 2 times 12 is 24, 24x. So I'm just going to write it on the side here. Our final answer is that our third derivative is equal to 24x. Okay, now that we've worked through some examples on our own, here are 4 questions for you to try on your own. The first 3 ask you to find the second derivative of the given functions, and then problem 4 asked you to practice doing higher order derivatives, in this case asking you for the third derivative. So the answers to these questions will appear in 5 seconds. Okay, so for the first question, you should have gotten that the second derivative was 48x plus 2. For the second problem, you should have gotten that the second derivative was 1 over x. For the third problem, you should have gotten that the second derivative was e to the sine x times cos squared of x, and then minus e to the sine of x times sine of x. And then finally, for problem 4, you should have gotten that the third derivative was 6 minus cosine x. If you have any questions, feel free to leave them in the comments below. Thank you so much for watching. Have a great day.